All right, let's get started. So, one of the things I got the most requests for was a video about looking at a solution reaction. So, what we're going to do is take the overall thermodynamics of this reaction as a case study to go back and forth from enthalpy and entropy and to solubility. And from solubility, we'll look and see how the effective temperature and all that. So let's start by looking at the two ions here. We know that we can predict trends in the entropy of solution for different ions, but we can't predict the overall sign. Why? When we look at these ions, we know that the ions are going to be free to swim around, but they also are going to form ion dipole interactions with water, and those ion dipole interactions are going to orient the water and decrease the entropy of the water. So we can't predict the sign of delta S. We also can't predict the sign of delta H because we're breaking apart the salt. That costs energy, but making ion dipole interactions releases energy. What about trends though? So if we look at this group of salts here, we know we've got salt, we're breaking apart a salt and forming ion dipole interactions, and those ion dipole interactions are going to be stronger with a salt of greater charge density. So on the enthalpy side, what does that mean? Well, the energy cost to blow apart a salt is higher when it's got higher charge density, but so is the energy payback. So we can't predict trends there. But what about the entropy? Well, if we look at the entropy for this reaction, we see that, oh wait, we can do some trends. We can see that the silver fluoride is going to decrease the entropy of the water the most because it has the highest charge density. And why is that? Well, that small fluoride ion is going to get closer to the water than the big iodide ion. And so, though we can't predict the sign of delta S of solution, we can say that the least favorable delta S of solution is going to be the silver fluoride because it's just decreasing the entropy of the water the most, and the most favorable would be silver iodide. So for that reason, there'd be a trend that the most soluble salt out of all of those would be based on the most favorable entropy of that reaction would be for silver iodide, not silver fluoride, because silver fluoride is going to decrease the entropy of the water more because of its higher charge density. So the only trend we can get from periodic trends is a trend in delta S of solution. So if you calculate this based on data that we have in the appendix, you'll see that silver fluoride is going to be the salt with the highest, least favorable delta S of solution, and silver iodide will be the most. Let's look at a couple other reactions that are involved with salt thermodynamics and see if we can come up with a prediction of the sign. So the lattice enthalpy is the energy involved in taking the salt and just blowing it up into gas phase ions. So we know that we're breaking up ion dipole interactions and we're not getting anything back in return. So it's just costing us energy. So we know this is going to be endothermic. We also can look at trends in the lattice enthalpy because, as we expect, a higher charge density is going to give us a bigger lattice enthalpy. So that is something we can predict, not just that it's going to be endothermic, but which salts in a series are going to have a bigger lattice enthalpy, so if they have more charge density. So the max one would be the silver fluoride again because of the small size of the fluoride ion. All right, let's look at hydration enthalpy now. So hydration enthalpy, we're taking gas phase ions, and we're going to take those gas phase ions and we're going to have them dissolve into water. And so here we don't have any interactions on the left-hand side, but then we're going to make ion dipole interactions on the right-hand side. And so that is going to be giving us off energy since we're making interactions. So we know that we're going to get ion dipole interactions. So anyways, we're making interactions, we're not breaking any, so it's going to be exothermic. And we could also look at periodic trends there and say, well, the smaller the ions, the more strongly they're going to interact with water. So if we were going to try to predict, we would look at the charge density. Now we have to be careful when we're talking about which one's bigger. We're talking about absolute value here, since we're talking about the size of a negative number when it comes to hydration enthalpy. So the bigger negative number, the bigger magnitude would be the hydration enthalpy for silver fluoride because it has the biggest charge density. Let's use the data we have. Let's look at some data and see if we can come up with a numerical answer to how soluble this salt is in pure water at room temperature. And then we'll move on and see how soluble it is at a different temperature. So we'll actually look at the Van Hoff equation. So let's start by looking up some data. So this is all data we can get by looking at those PDFs in the posted in Canvas. So we looked up the heat of formation of the different species in the reaction and the delta S's for the different things in the reaction. All right, so let's write out the reaction first, and then we can do products minus reactants to figure out delta H and delta S for this reaction. And before we do this, let's set up a roadmap of where we want to go, which is solubility, and how we're going to get there. So we know that we could get solubility if we had the equilibrium constant for the reaction of dissolving this salt. And how could we get K? We could get K equilibrium. Notice this is KSP. There's a bunch of different flavors of K, and they'll just have different subscripts, but they're all just K equilibrium. They're all just different equilibrium constant. We could get that from delta G standard. So we could get delta G standard if we had values for delta S standard and delta H standard. And we can get that because we have data. So before you do any kind of problem, you should sort of lay out a little roadmap showing what you have, where you want to go, what the intermediate steps are, before you get lost in the details. Maybe write that at the top of your paper that you're working on. Okay, so now what we're doing is we're going to do the heat of reaction by doing the heat of formation of products minus reactants. So we write these down, and we've got our products being the iodide and the silver, and our reactant being the silver iodide. And these are all going to be in kilojoules per mole. So we write these out. And when we plug all this in, we get that the delta H for this reaction is going to be positive. It's going to be a positive 112 kilojoules per mole. And notice that this is a positive number. It's an endothermic reaction. And this answers the question, like, why is silver chloride so insoluble, or silver iodide, why is it so insoluble? We've got this giant enthalpy of reaction that's positive that we've got to overcome to dissolve this salt. So we're going to repeat the same process for the entropy of reaction. So we look up our data. This time it's in joules per K per mole, since it's entropy numbers. And when we're done, we're going to see that this reaction actually has a favorable entropy. It's got a positive delta S standard for forming the solution. And this shouldn't be that surprising. We couldn't have predicted the sign, but we're not surprised that it's positive because we have some ions here, especially the iodide, that does not have a iodide's a really big, it's a huge ion, so it has a really low charge density. And so we're not surprised that, actually that shows up in the entropy numbers on screen there, that forming aqueous iodide solution, that is going to contribute to an increase in entropy because of its low charge density. So we've got a reaction that's favored by entropy but disfavored by enthalpy. And to figure out like what dominates at a particular temperature, we've got to do delta G is equal to delta H minus T delta S. So let me erase that. I'm just going to write in the equation before I put any numbers in. I probably should do that every time. So delta H minus T delta S. And let's go ahead and put those numbers in. So we've got a positive 112. We better convert that from kilojoules to joules because we want to make sure that we don't try to add kilojoules to joules. So we're going to convert this to joules per mole. The other thing we want to make sure we do is plug in kelvins here for our temperature. Our entropy is given in joules per mole per Kelvin, and so if we don't use kelvins, that's not going to work out either. So basically, unless you're absolutely positive that you can use Celsius, it's safer just to use joules. And so we've got our positive entropy of 68.4 joules per mole per Kelvin. I've got 298 kelvins. Multiply that out, cancel my kelvins, so I'm adding joules per mole to joules per mole, and I'm going to get my delta G standard. And when we go ahead and punch all this in, we end up with a positive number. Okay, so this is going to come up to be a positive 91,800 joules per mole, or we could say it's 91.8 kilojoules per mole, but it's a positive number. So this delta G standard is positive. Now let's pause and say, like, what does that mean conceptually? So what this means is that we're going to have an unfavorable equilibrium. We're going to have an unfavorable equilibrium constant. So we know K is going to be less than 1. Okay, that's what delta G standard means. And so you want to equate those two things in your head. That yeah, small equilibrium constant means a positive delta G standard. So what does that mean? It means I'm going to have a lot of reactant, or a high concentration of reactants at equilibrium, more reactants than products. Okay, so this, we say it's a reactant favored reaction or an unfavorable reaction, however you want to put it, that the concentration of reactants will be higher than products at equilibrium. That doesn't mean that it's spontaneous or not spontaneous, because that's talking about a specific scenario. So when I first start, if I take 3 femtograms of silver iodide in pure water, it will dissolve. That's spontaneous. But what happens? As I increase the concentration to a slightly higher number, eventually I'm going to reach equilibrium and no more is going to dissolve. It's going to fall to the bottom. Okay, so this idea of having positive delta G standard and small k means that the overall process is one where we're not going to progress very far towards product. All right, well now let's go back and look at our roadmap. So we've got our delta G standards, so now we can calculate our KSP with it and then find our solubility. Let's do that. All right, let's calculate an equilibrium constant from this delta G standard. So we have an unfavorable delta G standard, so we expect to a small equilibrium constant. So let's see if that's so. And since we know what we're getting before we start, we'll be able to check our work. So delta G standard is going to be equal to negative RT log of K equilibrium. That's true for any type of equilibrium constant. It really doesn't matter whether it's a Ka, Kb, or whatever. Any equilibrium constant is going to be related to delta G standard this way. So let's solve for K. So we want to get rid of the logarithm. So first we'll just divide both sides by RT. And we want to be careful here and convert our kilojoules into joules, because our RT is going to be in joules. So divide both sides by negative RT. That'll give us the logarithm of K. And then we're going to take the inverse log, or the exponential function of both sides. That'll get rid of our logarithm. So we're going to have just K on one side and the exponential of negative delta G standard over RT on the left-hand side. Great. So now we can just plug in our numbers and we're ready to go. So we'll just do that over here on the right-hand side. So we've got E to the, want to be careful, put this in joules. So that is a, because we want to cancel the joules on the bottom, we also want to watch that negative sign there. So we've got a negative 91,800 joules per mole on the top. So it's pretty easy to make a sign error there, so just watch yourself. So we have joules per mole. On the bottom we have 8.314 because we want to use the correct R that's going to have units of joules to cancel the joules on the top. And we've got our temperature, which is, well, we wanted to figure out the solubility in room temperature water, so let's do this at 298. Great. So let's plug all that in, and we'll get our K equilibrium, and we expected a small number, and we get 8.0 times 10 to the negative 17th. So this is obviously a really tiny K, so not a very soluble salt. We wanted to find the solubility in pure water. So if we say what's the concentration of a saturated solution, or if we say what's the solubility, those are the same thing. That's asking the same question. So in a saturated solution, in other words, if we took silver iodide and shook it up, and so we had excess solid on the bottom, but we had also, it was in equilibrium with a little bit of dissolved stuff, and we say what's the concentration of the dissolved stuff, that would be the solubility. Okay, so let's go ahead and do this. To do this, we need to write the equilibrium constant for this reaction. So to do this, we're going to write the equilibrium for the constant for the reaction, and we have to be careful that we distinguish between the equilibrium constant and the reaction quotient. And we also have to we're going to use the relationship here that every mole of silver ions is going to also produce a mole of iodide ions. So those are going to be produced, that's not a separate variable, those are going to be produced in the same amounts. So if we write the reaction quotient and the equilibrium constant, we can see that they're both going to be a function of the product's concentration. And we're not going to have the reactant concentration. Why? Because it's a pure solid. So pure solids and liquids never appear in K and Q. And the reason is that they don't have a concentration. They're not solutes, and so they don't have a concentration that can be varied like the solutes do. So those are just going to be plugged in as a 1, or normally we just omit them because plugging in a 1 doesn't have any numerical effect. Write the expression for Q. It's going to be the concentration of silver times the concentration of iodide. And the exponents on here are just 1s because the stoichiometric coefficients in the balanced reaction were just 1. And if we write K, it looks exactly the same. And it's not the same, so we really should be careful and say that we should put notation on these to say that we're talking about equilibrium concentrations, because K is a constant, right? Those are, at equilibrium, what are these concentrations of iodide and silver? And if you multiply those, you get a K, which is a constant. It doesn't vary. But Q is any number, right? We could have pure water. And if you had pure water, then Q would be equal to 0 for this reaction. And then it would slowly increase as we slowly added a little bit more, as we dissolved a little bit more salt. So Q varies during the reaction as it progresses. It's slow. If you progress to the right, it slowly gets bigger. K doesn't. K is fixed. So keep those two very, very distinct in your head. At this point, you might think that you can't solve for those concentrations because you've got two variables. So you're going to remind yourself that those were produced in 1-to-1 ratio. So it's a single variable. Let's call it x to remind ourselves that they have to be the same number. So we say x squared is equal to k, and now we can just solve for the concentration of those ions. So it's going to be the square root of k. And so we get that the solubility of this salt is going to be really small, right? Because we're taking the square root of something that's 10⁻17. So we can see it's actually going to come out to be, the square root of this is going to end up to be 8.0, so it's 8.0 10⁻17. Take the square root of that, we're going to get 8.9 nanomolar. So this is a really tiny concentration, right? Because you're used to, even the dye solutions that you did were pretty dilute. Those were micromolar. So this is more than 1,000 times less. So this is really, really dilute. So not a very soluble salt, which is what we expected. Now let's figure out what the solubility of the salt is in boiling water. So this is going to give us a chance to use the Van Hoff equation. So I derived the Van Hoff equation, and then I showed you two different forms, the graphing form and the two-point form in the other videos for this week. So this is an occasion for the two-point form, right? Because we have the equilibrium constant at one temperature. We want to have it at a different temperature. So let's go ahead and write this out. So we've got minus delta H, standard for the reaction. That tells us how rapidly it varies with temperature. And then we have the reciprocal temperatures here. Now be a little bit careful. Delta, the difference between 1 over T1 and 1 over T2 is not 1 over delta T. That's a really common mistake. Don't do that. It doesn't, the math's not right. Okay. Let's go ahead and solve this. So we'll take the exponential of both sides to isolate the K ratio. So we've got minus delta H over R times the 1 over T2 minus 1 over T1. And we already have, as I said, T1, T2 is our boiling water temperature. The only thing that's unknown is our K. So we're just going to solve for that second K, the K at that new temperature. So we multiply both sides by the K at the original temperature. And we're going to, yeah, I really want to emphasize that. Don't, it's a difference of reciprocals. It's not the reciprocal of a difference. Anyway, so you solve for K2. And now we're going to, once we've got the algebra done, we'll just plug in our numbers. And when you do this, things to watch out for, make sure once again your delta H that you put it back into joules instead of kilojoules. Make sure you use this right R, and make sure your temperatures in kelvins. Those are the only possible points of confusion. And just make sure that you have your ordered pairs straight, that you're pairing T1 with K at T1 and T2 with K at T2. So just make sure you don't switch those. Obviously, that would be a mistake. All right, so we're going to plug all that stuff in. And we've got a negative 112,000, so 112,200 joules per mole. That was the delta H standard that we calculated earlier. Oh, shoot, I just realized I made a mistake. That's delta H standard, not delta H. So all these are standards. We've got a reciprocal 1 over T2, which is 373 Kelvin minus 1 over 298 Kelvin. And now we can check our units. So we've got, on the bottom of our fraction, we have reciprocal kelvins. And then over here, on this difference area, we have reciprocal kelvins. And so the reciprocal kelvins are going to cancel those reciprocal kelvins over there. And then we've got joules on the top and the bottom. We also got moles, so we're going to cancel our moles with our moles and our joules with our joules. Let's go ahead and cancel those joules, cancel the moles. And now we're unitless. And we have to be unitless because we're about to plug into an exponential. You can't take the exponential of something with units. So that's another way to check your work halfway through a problem, or check your algebra, is to see, oh, did I have units in here? And you shouldn't. It should be unitless. So anyway, when we plug this in, our new K comes up to 7.3 times 10 to the negative 16. So we increase quite a bit on the size of our K.